This webinar is entitled Building Better Designs with SOLIDWORKS Flow Simulation. And it's going to be presented by myself, I'm Dane, and my colleague Damon as well. So a little bit about myself. My name's Dane, and I'm going to kind of guide you through the first half of the presentation. My background's in mechanical engineering, and I received my degree from the University of Alberta. So that's up in Canada for anyone that's wondering. And I have about 6 years of experience as a senior applications engineer here for Hawkridge Systems, which is basically means I exclusively work with SOLIDWORKS, and I'm a certified mechanical design expert and simulation professional. So I am working from home today, so I apologize in advance if my two assistants cause a little bit of a disturbance today. Sometimes they like to get a little bit yappy. So I'm going to be doing the first half of the presentation. On the back half, my esteemed colleague Damon is going to be presenting everything in flow simulation. So he's got a bachelor's of science in aerospace engineering, which is great for external flow. He's actually the project manager for plastic and flow simulation, and he's been with Hawkridge basically forever, 13 years. And he's a certified SOLIDWORKS expert, a lead AE, with the specialist in flow, HVAC, electronics, cooling, all of that stuff. So he's the guy to talk to. Sorry, Damon, go ahead.
No, thanks for the introduction, Dan. It's great to be here. I think we're going to cover some really interesting use cases for SOLIDWORKS and the CFD add-in that maybe are different than the traditional, mechanical or aerospace design that maybe we're used to in the past. So this should be exciting.
Nice. All right. So can SOLIDWORKS design validation lead to a more civil workplace? So I love this title. Makes me giggle every time. I tried to say it with a straight face, but I couldn't. So what the problem is that we're going to try and pose to you today and pose a solution for is that modern building designs must keep occupants happy and minimize energy consumption as well. So we can't just always go more HVAC, bigger fans, just make everything bigger. We got to try and conserve energy, be efficient, reduce heat loss, things like that. Find areas where we're losing heat, or well, I'm up in Canada, so it's always about losing heat, but sometimes it's the opposite. Heat coming in, things like that. So 2D floor layouts are good for architecture and building it, but it's not a guarantee of good construction. So if you use a parametric CAD tool to create a fully detailed 3D model, you can validate actually for heating, cooling, ventilation, and find some problems you might not see until after construction when it's too late to fix anything. So this is the whole portfolio that we offer here at Hawkridge. Bunch of design software, managing your data software, simulation, and manufacturing, the whole kit and caboodle. We also offer services and stuff like that, but today we're mostly going to focus in on flow simulation, so just this one tiny box, and then some SOLIDWORKS design as well. So the nice thing is that the design environment and the simulation environment are going to be the same, so then there's no importing, exporting, everything's going to work really smoothly, and we can validate while we're designing. So I'm going to start off with the SOLIDWORKS portion, and then I'm going to hand that off to Damon. So there's two modules that I'm really going to focus in on SOLIDWORKS, and that's the weldments and routing module. So I'm going to use weldments to build my building, and then I'm going to use routing to build my HVAC in the building, and then we're going to pass that off to Damon, and he's going to simulate it for us. So weldments are a special type of part model containing multi-bodies, which can be described with a cut list. Oftentimes, these bodies are welded together in production to form a frame. Weldments use multi-body parts for easy manipulation and to minimize complex file relationships. To create a weldment, all you do is sketch out a skeleton frame, choose your standard profile, and use the corner management tools to get the perfect connections. So a library of standardized profiles is included in every license of SOLIDWORKS. They include many standards, including ANSI, Inch, and ISO, and each standard comes with a library of members that are designed to the specific standard. They're the sizes you can buy off the shelf and the sizes that have been included in many codes and design standards. So you don't have to reinvent the wheel, the library is already there for you. So each member type has many sizes, which is easily obtainable in a selection box. You can also go back and change the file of all or selected members of any stage in the design. So if you're trying to iterate after you run your validation, there's just a nice drop down where you can change your sizes and everything updates and follows suit. If these standard sizes don't work for you, you can customize these standards or make your own unique profiles for use in your designs. So the design process is easy. First, you draw your skeleton frame. You can use 3D sketching tools or a series of 2D sketches. And a nice little tip is you can split your longer segments into standard lengths. So using sketch tools like segment or split entities. And the reason you'd want to do this is this helps down the road for cataloging the total numbers of members that are needed. So if you buy your structural members in standard lengths, then you can segment your sketches, and then that's going to be cataloged all the way as you design and make your changes. So as you create the structural members, there's some corner management tools that allow you to control the shape at the corners. So corner treatments can be applied globally, or each local corner can be controlled independently. You can add weld gaps and change the cut order to get the exact shape you desire. There's a specific trim extend tool which can be used to add or remove material and create corner blends between different sized structural members. So with weldments, you can get the corners looking exactly the way you need. So while you're modeling, SOLIDWORKS is tabulating information about your structural members. It uses that information to sort them by size and shape. The cut list will give you information like the length of the member, how many members are at that length, the total length of that member needed for the entire part. So you can use this information to quote, order, or display on a drawing file. You can even put in custom properties like maybe a part number, a finish, or really anything you need specific to your job. So for our example today, I'm going to construct this modular building. So it's something you can construct on the back of a trailer, or maybe on site, you get a foundation poured and then you build this little modular building, and you can take it apart and rechange its size, configuration. It's all modular and meant to be put together. So since it's modular and made up, I kind of made some custom profiles for all the different bodies that I have. So I got some floor channels, wall joists, corner posts, and they're all a custom weldment profile. So this isn't out of the box stuff, this is stuff I made. So I'm going to utilize patterns at the sketch and the part level to quickly and easily repeat some of these wall sections. So these standard pieces have been designed to fit together, so I'm not going to need to do any trimming or extra cutting. So when I'm done, I'm going to get a full count of all the components I need, which components might need some cuts, and I'm going to have the ability to display all of that information in my SOLIDWORKS cut list. So I'm in SOLIDWORKS here. I have my skeleton frame already pre-sketched for us, so you guys don't have to watch me do that. And I'm going to go into the Weldment tab into my structural members. So all of my standards are here, but I've made my own standard for my modular framing. And I'm going to start off just with my floor channels. And I'm going to go around the perimeter, and these floor channels come in 12-foot segments. So I went down to my sketch here and I segmented my floor channels into 12-foot lengths. And I can see SOLIDWORKS is putting in the miter right in the corner for my channel. That's what I need for my corner post to sit in there nicely. And that's pretty easy. The next piece I'm going to add in there is that corner post. So I can go back into my weldments tool and I'm just going to change my type. So I'm going to go to my corner post and it's telling me I need to pick a size. So sorry about that, SOLIDWORKS. Thanks for the reminder. And looking at my corner post, I can see that it is fitting very nicely in my channel. It's as if I designed it that way. And just add my next piece. So now that I have this corner post, I can start building my walls along the edge there. So I have those as a structural member as well. So I'm going to come in and I'm going to grab my wall panels. and I'm going to start placing them. So I'm going to grab that same sketch line again so I can reuse that same 3D sketch geometry, even though it does get consumed. And this is not quite facing the right way, so I can rotate all of my members and all of my profiles. So I'm going to rotate my wall panel here, and it's still not quite setting up. So this line that I'm using isn't aligning properly with my wall panel, so I can use my locate profile tool, and I can come in here and realign this, and now it's sitting really nicely just the way that I want it. So I'm going to use what's called a selection set. So I've pre-selected all of my wall posts, and this is going to save me from having to go into the graphics area and keep grabbing all of those. So I can just shift select them from my menu from this pre-selection that I saved. So I grabbed them all once, then I saved it as a selection set. It's a really great technique if you have repetitive selections that you always need to be grabbing. So my wall panels are up there, but I'm missing my wall joist that these panels kind of slide into in this modular form here. So again, I have those as a structural member. So I'm going to grab my wall joist, grab my size, and again, I'm going to use this nice selection manager here to grab everything that I need. And they will all propagate for me in here. Now, they need to be rotated again. They're facing the wrong orientation, so I can come in here, rotate my profile, and they fit like a glove. So now I'm just going to use some symmetry because my back wall is going to look identical to this. So I'm just going to use my mirror tool, and this is where my cut list is going to come into play because I'm going to mirror all these bodies. But instead of me clicking on every single body, I'm just going to use my cut list to pull them all over. But before I do that, I'm just going to get my wall joist on the other side, or my corner post, because I never put them in there. So now I'm going to mirror this entire wall and plop it over there. So I'm going to use my cut list, and you can see my cut list is already organizing all of my components. I have all of my floor channels, so I do need to mirror over my 2 corner posts, all of my wall panels, and then my wall joists as well. So this cut list is organizing all of my bodies, and it really helps me with patterning and using symmetry. So I want to mirror these about my front plane, and now I have my other exterior wall. So I'm going to repeat that process again here for my little wall on the side, the wall on the back, and all of those walls in the middle. And then finally, I'll end up with my fully completed building here, built with the weldments. So in the end, I have this cut list, and I can see that I have 4 12-foot corner posts. I got 42 of my wall panels that I need. I got 38 of my wall joists. Then I have my 8-foot walls, and some of these floor channels need some specific cuts. So you can see right here, my floor channel 5 gets highlighted in orange. It's a really little one. So I can look at the properties that SOLIDWORKS is calculating in the background, and it's telling me exactly how long it needs to be and what angle the miter needs to be for my wall to actually be constructed. So SOLIDWORKS is categorizing and cataloging all of this information, and of course it updates as I make my design changes. So all of these little floor channels that have all these custom cuts and aren't the standard lengths are all categorized here, and I can put that in a drawing, bill of materials, print it out, item list, use it for ordering, whatever I need to do. So now that I got my building constructed, what we're going to look at is actually building the HVAC system. So the routing module in SOLIDWORKS Premium can make routes for a variety of applications, including HVAC, piping, tubing, and electrical. So SOLIDWORKS Premium includes a library of fittings and components of many sizes for these mentioned applications. You can always create your own custom components if the library doesn't have exactly what you're looking for. So with routing, you can drag and drop fittings, and the appropriate sized routes will begin to be generated. You can continue the route line with hard corners, and the appropriate joints and transitions will be added based on specified components. So in the end, SolidWorks is again categorizing all the lengths of your routes, the total length of all of your route members, the number of elbows and other components, and it's organizing them into a sub-assembly. So the routing library that comes with SolidWorks includes many standards, including ANSI, ASME. You can find components for HVAC, piping, tubing, conduits, electrical, and it comes with your standard transitions like 90-degree elbows, T's, reducers, many more. And if you can't find what you're looking for, you can always make your own routing components with all the benefits of routing. So as you drag and drop components, the route will automatically be started. From the endpoint, you can use the auto route tool, or you can just connect two ends of the sketch with your own route path. So as you make these hard corners, it transitions automatically to the radius for the available bend of the components that you've chosen. So now what I'm going to do is I'm going to kind of finish off the little HVAC system that I have and then pass it on over to Damon for doing a CFD analysis on these components here. So here's my HVAC, and I gotta make sure I have my routing module turned on, which I do, so that's good. And we can see that my HVAC system or my route has been categorized into a sub-assembly. And inside of this sub-assembly, we can see that it has the components. So all of my T-joints, my reducer in here, my diffusers, and then the route parts, the actual ductwork itself. So for all of this ductwork, once I get the screen the right size over here, we can see that each one of them has their own specific length, and SolidWorks is continually categorizing that for us. And if I make any design changes, those will update, and wherever I'm referencing that information, it will get updated as well. So there is a template that you set up for your routes, and that's inside of your route properties. So for this route that I made, I'm going to be using this specific round ducting with these properties. And every time I have a bend, I'm going to use a 90-degree elbow. So you can have 245s or you can use different elbow types, but I'm going to go ahead with the 90, keep it nice and simple, and keep my HVAC system under the roof there. So all of those route properties kind of define what components SolidWorks is going to choose for you. So inside of your design library, again, there's a routing library for conduits, electrical, HVAC, piping, tubing. Inside the HVAC, you do have your rectangular ductwork, but I chose round ducting for this design here. And then we have things like our 45 bend, 90 bend, T's, we have reducers, we have a square to round transition, we got our cross, the air vent. And these are all just the components that I used in the design here. So let's go ahead and let's finish it off. So I'm gonna edit my route. And that brings you inside of a sketch. So basically everywhere that I have a sketch line, it's going to start adding the geometry. So there's a route point here, and the route point is basically saying this component has a route, and this is where you can start doing your auto route, but I'm just gonna add to the route here. And this line right here is going to determine where my ductwork is going. So I had this pre-sketch of how I imagined it was gonna look like, and that's making my life really easy now in routing because I can basically just follow it. So as I transition with this hard 90-degree sharp, we can see SolidWorks automatically puts in the round with the appropriate bend radius. And once I leave my sketch here, it has added that to the components folder. So this elbow right here has been added to the components folder. This length of route has been added to the route folder, and its length has been categorized as well. So it is all in there, all calculating, and then as I make changes to it, it'll update all of that information. Now, the nice thing about having it in its own unique subassembly is that I can really easily isolate my HVAC system. And I can come in here, I can evaluate it, see if I have any choke points, and then once we start validating, see where I need to maybe make some ducts wider, reducers, all that good stuff. So now that we've kind of made our modular building here, I'm going to pass it over to Damon, and he's going to run some flow analysis to make sure that I made this ductwork big enough for it to be comfortable to actually work in here and for human inhabitation.
Cool, thanks, Dane. So yeah, so that was honestly a great recap of how, really in most cases, it's going to take a lot less time to create one of these sort of architecture-based or structural-based designs than you might expect if you are used to doing things like traditional cast part or injection molded part design in SolidWorks with solid features. And for anybody that maybe has used analysis tools in the past, it might also be surprising that you can use these kinds of detailed features and build a model that has things like, an actual square tube weldment profile in it that's hollowed out and everything, and use that for your analysis. But that is one of the sort of benefits of not only the fact that SolidWorks analysis tools are integrated into the same CAD environment, but in most cases, the meshing tools that they have, particularly with the one we're going to talk about here, can handle those kinds of details. So we don't need to start from scratch and try to recreate this entire building with some simple extrude feature or or a sweep. We can use the actual geometry coming from routing, coming from weldments, and that way our analysis will be even more realistic. So again, as Dane mentioned, the portfolio of tools that we sell and support at Hawk Ridge covers the design side, but it also covers the simulation side. And we have a variety of structural analysis tools, thermal analysis, fluid flow, really depending on what kind of CAD environment you're working with and what your design process looks like, and what you want to validate the design for. We probably have a tool that can handle the job in most cases. And so in this case, because our biggest concern with the building design is airflow and the related heat transfer from that HVAC system, what we're probably most interested in is a tool that can perform that thermal and fluid flow analysis, which in many cases is really the same analysis, right? We want what is more or less a multi-physics simulation, because the fluid flow, such as the air coming out of an HVAC system, is probably the biggest factor in how hot something gets, how hot a room is, or if if someone's sitting directly under a vent and feeling too cold, that kind of thing. But just be aware, of course, that whether it's SolidWorks simulation or Simulia Abacus or even Simulia CST Studio, we have tools to do other kinds of analysis too, just on this that might be useful on the building, structural analysis, communications, high frequency RF, that kind of thing. I know somebody had mentioned in the questions earlier that they were interested in using a flow simulation or CFD tool for injection molding. You could simulate something like a molten plastic in the product that we're going to be looking at today, but if your goal is to actually simulate a plastic injection molding process, there's a different tool we have specifically for that called SolidWorks Plastics, and you can see in the questions panel there, I put a link into our website where you can get some more info on that. But when it comes to most fluid flow and thermal analysis applications, the best product, sort of what we call our go-to or our flagship for that, is SolidWorks Flow Simulation. So this is what we call a general purpose CFD or computational fluid dynamics tool that's built into the SolidWorks and can be used for almost any type of either internal or external fluid flow, whether that could be a gas like airflow in an HVAC system, liquids like water in a piping layout, or even downhole applications. And it also can handle thermal analysis and do the heat transfer that might be related to this fluid flow. The aspects of this that make it so useful for these applications is the CAD integration, the ability for this tool to sort of automatically detect where the fluid space is in your SolidWorks model, and also the fact that the mesher can handle the types of models that we typically create in SolidWorks, such as what Dane just showed us, using things like the weldment features and not having to go back and build some sort of overly simplified solid model specifically for FEA. So we're going to take a look at a couple different ways you could use flow simulation in this sort of building design environment. But when you're deciding whether to create a new simulation on one of these designs, typically one of the first things you have to choose or decide is what the scope of the analysis should be. Where are you actually interested in looking at the fluid flow in your design? For example, if it was some kind of electronics container, you might only be concerned about the airflow patterns on the inside of that container at first, in which case you could do an internal analysis and look at where the air from a fan is going. But if you're more interested in maybe the surrounding environment of the box as well, and maybe how airflow gets in and out of the different vents, or maybe corner treatments of a sheet metal box, we could do an external analysis too. So we can do both in this software, and I'll show you examples of both of those as it would apply to this modular building that we've created. And really the most important thing to keep in mind is, because SOLIDWORKS Flow Simulation is integrated into the CAD tool, it's something that's meant to be used throughout the design process, not just as an afterthought once you've spent hours and hours creating a detailed model. For example, if as Dane showed us, if you were in the middle of trying to lay out the HVAC ducting with the routing tools and you hadn't finished detailing the rest of the weldment structure yet, but you wanted to start getting an idea of whether the ducting sizes were correct in the HVAC system, or what kind of flow rate you would need, you could run an internal fluid flow analysis with SOLIDWORKS Flow Simulation to check that out. And obviously, as you continue detailing the design, modifying the design, adding more to it, you could continually run that analysis to see what's happening and get that sort of instant feedback about the design. So maybe in this case, the first question we would ask ourselves is, what kind of a flow rate do we really need coming from the blower in the HVAC system, right? What happens if we try to up the flow rate? Do we get even distribution to the different vents in the building? Do we start to run into any kind of back pressure concerns where the piping or the ductwork doesn't allow for any more flow? So we can run a basic simulation just to look at the fluid flow side of things for starters before we worry about heat transfer, and then we can go on after that. So let's look at an example of how this would be done in SOLIDWORKS Flow Simulation. I'm gonna pop over to SOLIDWORKS here, and I've got the same HVAC assembly that Dane created. This current version is really just the external structure with the dividers on the side for each room, and then of course the HVAC ducting. So we haven't finished detailing it yet. We haven't put in the furniture or windows or things like that, but that's okay, because for right now I'm just going to focus on analyzing the ductwork. And so if that's my interest, I probably don't really care about the rest of the building layout yet. So I can do a configuration where I get rid of the other stuff that I'm not interested in, and I can focus in on what I'm trying to analyze. Of course, if I hadn't done that yet, it would be as simple as adding a new configuration here and suppressing the components that I'm not interested in, or hiding them. And so then when I'm ready to perform an analysis in SOLIDWORKS Flow Simulation, the only thing I might need to do to the geometry in order to run something is to create what we call lids. Obviously, in some cases, you may need to simplify, or you may want to simplify the assemblies that you created. There might be components that are irrelevant, or really, really detailed parts that you want to get rid of because they're not important to the analysis. But that's sort of up to the user's discretion. What you will have to do as far as the geometry is, if it's an internal analysis that you're trying to perform, you'll need to create what we call lids, so that SOLIDWORKS Flow Simulation can detect where this internal fluid space is that you're trying to simulate, and that way it won't include any unnecessary parts of the system, and more importantly, those lids will give you a location to apply what we call boundary conditions. So, flow rates, pressures, or whatever other fluid parameters you want to define about the analysis. So, for example, here with the HVAC ductwork, maybe I'm not even concerned about the actual HVAC vents yet. I could hide those too. And basically, if I want to simulate just the insert side of the ductwork and have my outlet be at the end here, I just need to cap that off, and there are a couple ways to do it. The first is I could create what's called a lid, and I can do that with the lids tool, the create lids tool, which is something that comes in SOLIDWORKS Flow Simulation when you've enabled that add-in from the command manager in SOLIDWORKS. So basically you can turn on the button to pull the license for Flow Simulation, and then you can go right here to the tools dropdown and say create lids. And basically anywhere you've got a flat face that might be an inlet or outlet of the system, you just click on that face, and then SOLIDWORKS Flow Simulation will detect that and try to fill it in for you. And there are different ways to do it. I could try to seal off, the entire bottom of the simulation at once, all of the holes at once. I could tell it to just seal off one of these openings at a time, like so. And alternatively, I could also tell it to, I could choose to not use the create lids tool and basically model them myself. So I could, for example, just go over this other configuration here where I've isolated the HVAC system and just make an extrude. This is an assembly, so I could use your typical in context part creation methods that you would use in SOLIDWORKS, and I could just make a new part and make a little sketch, create an extrude, and there's my lid. And to be honest, if you have the time for it, this is often the better way, because now you'll have a fully parametric part that's associated to the ductwork in this case, and it'll move around and update with any design changes like you would expect. And so once you create those lids, again, with whatever method you feel comfortable with, you can then verify that you've done it correctly and that Flow Simulation is detecting this internal fluid cavity with this check geometry tool. Just click that button here, and we click the button at the bottom called Show Fluid Volume, and it'll scan the model and make sure that we have a sealed fluid space. And if we do, it will tell me what the volume of that fluid space is and show me where the airflow will be on the screen. So again, if as long as I'm only interested in what happens up to the outlets or up to the vents of the HVAC system right now, this is great. So now that I know I've got my fluid space detected, I can create my analysis. In Flow Simulation, we call this a project. So generally, the best way to do that is to go to what we call the wizard here. And this is sort of just a series of screens that will take you through the most important steps in creating a new simulation. And of course, the first thing you got to do is just give it a name. So we could call this, sort of baseline ductwork. Maybe we are expecting to have, some kind of low flow rate like 650 CFM, something like that. And as you proceed through the wizard, you'll have some basic setup information to put in, like the unit system you want to use. You can choose any of the standard ones, of course, or customize them. Maybe we want to use SI units, but we want our temperature in Fahrenheit because we're dealing with an American customer. Maybe we want our pressure in something that the building industry is used to, like inches of mercury. Once we get that configured, then we can specify what physics we want the solver to account for when we're running the analysis. We already decided that for starters here, we want to just look at an internal simulation of the duct, so we can leave our analysis type set to internal to keep the scope there. And you can see then in the list below that there are some different physical features we could turn on. Most of them related to heat transfer, but if we're not interested in that yet, we could just leave those off and run a simple fluid flow simulation just to look at velocities and pressures and not worry about any temperatures of the ductwork or air temperatures. Now you'll notice, by the way, there is something here called time dependent, and just want to point out that basically in SOLIDWORKS Flow Simulation, all of your analyses by default will be what we call a steady state simulation, which shows you what the results would be if you just had constant flow rates, constant heat generation, and everything else was just sort of in equilibrium. But if you want to run a transient analysis where you see something start flowing from a steady air condition, or if you want to see something gradually heat up, or maybe even have like the exterior air temperature increase, as if you're trying to mimic, the sun rising in the sky, that can be done with a time-dependent analysis as well. Just keep that in mind. So for right now, we'll leave all that off and do just a basic airflow simulation. And of course, the next screen asks us to pick what fluid we want to simulate. So in this case, we can just double-click air from the library. Of course, there are other gases and liquids and other types of fluids we could pick from in the library, and we could add our own. We can put in some wall conditions, to specify the smoothness of the walls. If we had some cast parts or maybe something really rough like insulation, we could even put in some outer wall thermal conditions to specify heat loss. And then finally, we would put in our ambient conditions as well. What sort of environment is the ductwork operating in? And really, that would probably be the installation site for this modular building. What's the surrounding, pressure and temperature of the job site? You can actually specify that in a few different ways in SOLIDWORKS Flow Simulation. A couple of years back, we added the ability to define it by altitude. So if you know that you were up, at 4,000 feet, you can simply plug that in and it will look up a table to see what the drop in pressure and temperature would be. So once we have that finished, we get a project created here in our Flow Simulation tab on the feature tree. And at this point, we would then be able to go in and specify the detailed boundary conditions for the simulation. So for example, if I want to assume that I've got some kind of blower that's flowing air in upstream of the reducer there, I could click on my lid that I had created at that inlet point and define the flow rate a number of ways, mass flow rate, volume flow rate, velocity, whatever information I have about that unit and that I want to assume. So maybe I'd say it's an inlet volume flow rate and I've got 650 CFM. Of course, there's tons of options like that you could specify, such as the temperature of the incoming air or what the velocity profile of the air looks like when it comes in. There are some simple checkboxes like telling the flow that it's fully developed with a turbulent boundary layer. So everything you need to make it a realistic assumption of the real world condition. We also have the ability to define pressure boundary conditions for when we don't know what the flow rate is. So for example, in this situation, we obviously wouldn't know what kind of flow we're getting through each of these vents. That's part of what we're trying to find out. So we can define just the environmental pressure of the room where the vents are flowing into, and then the software will be able to calculate the other side of that equation. Will be able to tell us what the flow rate is. If you're just doing a simple fluid flow problem like this without any kind of heat transfer concerns, then that's probably all you really need from a boundary condition standpoint. Of course, there are lots of other conditions that we can define. We can define actual fan curves for the blower and porous materials for things like filters or other foams or membranes, things like that. But otherwise, what we can do at this point is run the simulation. And of course, that will generate the mesh automatically, which is going to be what we call a Cartesian mesh, something unique for a SOLIDWORKS Flow Simulation. It's part of the reason why it is really good at handling these kinds of detailed or thin wall geometries. And it'll immediately start calculating all the results, including what we specify under the goals folder, which are basically sensors. These are the most important results from our simulation that we're interested in, and it makes those particular results easy to track. And it also allows the solver to check for something called convergence, which basically is the confirmation that you've actually found the steady state result of the system. So I can go ahead and run my analysis right here. And since this is pretty simple geometry and I'm just using the default mesh settings, it's going to solve pretty quickly here. And as the solver is progressing, you'll see that these goals that I have created are kind of being plotted and they're adjusting as the solver calculates each iteration. And when all those goals level off and are no longer fluctuating, that's when the solver knows it's gotten convergence and I've got reliable results for this kind of a steady state behavior. So right away, for example, I've found that my maximum velocity in the ductwork is about 8 meters per second. Maybe I was worried about noise or excessive flow. And I've also found that my pressure in this case, which was at the inlet, was not much above ambient. So if I was concerned about some kind of back pressure problem or just too much delta P, I found already that that probably isn't an issue, at least at the current flow rate. And of course, in SOLIDWORKS flow simulation, then there are a huge variety of ways to see those results, visually, to evaluate the design and figure out if things are performing as expected and how you might want to change the design. For example, I can create something called a flow trajectories plot to show the three-dimensional path of the flow from either an inlet or an exit point, and I can color those streamlines with some sort of result like velocity. So for example, here I can find out right away that, of course, I've kind of got my highest velocity here right after that reducer, as I probably would expect. And then as the flow disperses throughout the system, I've got lower flow rates here on the front side of the building. And that might turn out to be an issue, especially because in this case, that's going to be where I need to have some windows in the building. So maybe the flow rate that I had initially estimated wasn't enough. Maybe 650 is not going to be enough. Maybe I also would want to go back and have Dane redo some of the routing work and increase the duct sizing on that side of the office. What I could do though is, in addition to just changing the model and hitting run, I can also create what's called a parametric study, which basically is like a batch run, and it allows me to run this project multiple times with different values for some of the input conditions. For example, I can go in here to my volume flow rate and just type in sort of a table of different flow rates that I would want to test. So here I'm doing like 650, 950, 1250, etc. Or I could also vary a dimension on the model. So for example, the length of one of these duct segments, or maybe the bend radius or anything like that. And then the parametric study will run all those configurations for me. And of course, I'll be able to look at the results in a table here side by side. So for example, I can see that as my flow rate goes up, so does my velocity, which you probably expect. And I can look at the visual results side by side as well. I've obviously got higher velocity here. And it looks like once I really start to get up to maybe this 1550 range, I'm getting a little more flow on the front side, but still less than the back, which means I probably do need to redo some of that routing work at some point. So this is a great way to compare different conditions, but also different design changes if you've got dimensions in your sketches or features that you want to modify. So that's how flow simulation is meant to guide the early stages of a part or subassembly design to really help you optimize stuff. But once you get further along and you have a more complete design, then of course you probably want to focus in on running a highly realistic simulation that has a lot more of the real world factors built into it. And so for example here, I've made another configuration of the modular building where I have added in some windows here, just some basic framing and glass windows. And I've also modeled in just a basic representation of the job site itself so that I can perform a fluid flow and heat transfer analysis of both the entire building and the surrounding environment, because I'm probably worried about how warm each room is getting, which is going to be influenced by not only the HVAC system, but the external air and sunlight, solar radiation that might be coming in. And so while you could do that type of thing with any license of SOLIDWORKS flow simulation, if there are certain aspects that you want to make sure you can include for added realism, such as the ability to predict the amount of heat, specifically the amount of solar radiation that makes it through a transparent object like a window, there are some added features that are specially designed for that and for really anything in the building industry in what we call the HVAC add-on module for SOLIDWORKS flow simulation. So this is a specialized module that is explicitly intended for simulating human environments, offices, buildings, server rooms, anything where those sort of large scale thermal effects are more important. Just so you're aware, there's also an add-on module meant for electronics cooling, things like circuit boards and the IC packages that might be placed on those. And that, of course, is another really common application for flow simulation. But in the building industry, the HVAC module is definitely the most relevant thing. And so again, in this type of application, if you're trying to look at the overall ventilation in the building and incorporate solar radiation, in particular, you'd need this HVAC module to see what happens when you've got some kind of a tinted window that is meant to try to keep out some of the solar radiation, but obviously won't keep it all out. Flow simulation will be able to actually calculate the absorptivity of the material and figure out, based on how thick it is and the material properties, how much radiation is it letting through, and also what part of the spectrum is it allowing through, right? Is it allowing infrared? Is it allowing UV, etc.? So the first thing I would do, of course, is create a project that looks at the entire building and the surrounding environment. So I would, in that case, want to do an external analysis, which would just be that radio button that we've selected back here in the wizard. And then I would turn on some of those other physics that I was interested in. So for example, heat conduction in all of the solid components, such as the framing and the structure, the steelwork. I would turn on radiation, and in particular, I would want to turn on solar radiation so that the analysis knows I've got sunlight coming in and hitting the building at a particular angle. And you can specify that angle manually, but there's also a pretty cool database where you can just pick a location and a date. So for example, I could simulate what the sunlight might have looked like in San Diego this morning. And of course, set what direction north is, that kind of thing. And of course, I can also account for the spectral characteristics. And we've got the spectrum, the radiation spectrum of normal daylight built into the library, so you won't have to put that in yourself. And that will be factored into what gets absorbed by the window and what makes it through. And of course, I can also turn on gravity, because in reality, I'm guessing that the warmer air will kind of collect at the top of the building, near the roof or near the ceiling, I should say, and of course, we'll want to see that effect. So with those factors turned on, we would, of course, have our boundary conditions like the flow rate that we had specified before. In this case, I've increased it to that higher value. And then since we're doing heat transfer now, we also want some other conditions such as the solid materials. I've got some wood framing on my windows. I've got my gravel defined. And then these windows here, which of course are just a tinted glass, these are defined not only as a solid material with the typical solid properties like thermal conductivity, but I can also, with the HVAC module, specify that it's an absorptive solid that partially blocks radiation. And there's the absorptivity property that you could specify. You can even do that at many different wavelengths. So for example, if you look up the absorptivity chart for the material and you see what that absorption coefficient is for infrared light or blue light or UV, you can plug it into this table here, and that will be, sort of the highest level of realism that you can get. So it'll know how much of that daylight spectrum and which parts of the spectrum get through. And of course, we can have some goals in like we did before, and other thermal conditions like, for example, radiative surface conditions, where, if I have like a painted surface here, for example, on the roof of the building, if it's painted white and it's meant to reflect most of that solar radiation, I can specify that and see how much of an impact that has on keeping out the heat. So of course, I would run this analysis too, and now I'd have a much more realistic simulation of the total airflow in the building, the heat transfer in the building, and also what we refer to as comfort parameters. So for example, I could look at a classic result like temperature, and I might see right away that, I've got a couple of these offices in the building here that are a little warmer than the others. I've got warmer temperature near the roof, as I probably expected. And of course, I've got my cool air coming from the ductwork in the HVAC system. But in the building industry, these, temperature by itself is not always enough information, because there are other factors such as, the speed of the airflow, the humidity level, the pressure. Those things also affect how comfortable people will feel. And so because of that, there are some special industry-specific parameters that we can plot, such as predicted mean vote, which incorporate all of those factors not just temperature, so that you can tell whether the average occupant would feel too hot or too cold. So here's PMV, predicted mean vote. You can see that near the ceiling there are a lot of areas that are a little too warm there, except for in some of the corner office, which might be okay. And there aren't too many areas where the average occupant would feel too cold. So that probably means it would be safe to up the flow rate of our HVAC system and not worry about the person sitting directly underneath the vent. And there are different ways to visualize these kinds of results in the software. Another way is called an ISO surface, which basically plots that result in 3D. And again, we can get the same type of information, but maybe see more clearly where those hot and cold zones are. So rather than guessing, how people will appreciate the environment, purely based on temperature, this calculates it per the industry standard. There are other ones like PPD, which is percent population dissatisfied, and other ones like local air quality index that are also useful. So of course, I can already tell that there are some areas of the building that are less efficient, that are not evenly cooled, that probably need an increase to the duct sizing, maybe a change to the layout of the interior. Of course, you're not limited to just visual results in flow simulation. We can look at a lot of numerical results too. For example, the surface parameters on the windows. And one of the cool things that I could see right away is that if I look at my goals, I'm getting a certain radiant flux through the windows. And in this case, it's an average of about 500 watts per meter squared. And if you are familiar with solar radiation, the typical value for that is more like 1,000, 1,200. So that's a great sign that we are managing to block some of that incoming sunlight, and we're not exposing the occupants to the entirety of that heat. The last thing we might want to look at when it comes to a large scale realistic analysis might be the external airflow, and maybe what we're concerned about there is not so much heat, but we might have a structural concern when it comes to wind loading. And that's something we can do with SOLIDWORKS flow simulation as well, because flow simulation, of course, calculates all of the pressures and forces on a structure. And in this example, what we would do is just choose to simulate a larger area around the building, and we would still be able to look at the same types of velocity results and vectors, and look at how the airflow is flowing around the structure. And we could, of course, get results like the forces on the structure itself, or even just certain areas like the window. And then we could even take those results, and if we were trying to perform a structural analysis based on that wind load to see if there was any deflection on the sidewall or deflection of the window, there is the capability where you can export that data directly to a static stress analysis in SOLIDWORKS simulation, where you could flip over to the other module, create your static study, define your fixtures and solid material properties, etc. And then instead of having to make a guess at what the force is from that wind, you would be able to directly import the wind loads from your CFD analysis and get a much more realistic stress simulation. So that's another workflow that incorporates both flow simulation and the ability to do a realistic large scale analysis, and then in this case, the structural tools. Of course, as these things get really complex, we expect that you may not know how to do those kinds of simulations out of the box, but that's where Hawk Ridge Systems has got a pretty large team with people like Dane and myself, and we pride ourselves on having the best practices down for how to perform these types of simulations, whether that's going through a training class or pointing you to the correct tutorial, or maybe a blog or a YouTube video that we've made at some point, so that you can understand the right assumptions to make. And we can even go all the way to performing an actual analysis for you with consulting services to get you started, and maybe have a baseline analysis for you to modify. So of course, if you have any interest in the products themselves or the services that we offer to support the products, contact your account manager. They can give you all the information on that. And as usual, our technical support team is always ready to assist, either with any of the existing SOLIDWORKS features that you're using, like weldments and routing that Dane showed you earlier, or of course any questions you have about flow simulation. I know we're about out of time here, so I appreciate everyone sticking with us and giving us your attention today. We hope it was informative. There will be a recorded version of this webinar on our YouTube channel within the next week. So if you want to revisit that, feel free to check it out and keep it in your favorites list of your browser. Otherwise, thanks again for your time. I hope you have a great rest of the week, and we'll see you next time.